Wonderful. I just want to remove the floating controls. Okay, now I'm good to go. So thank you for inviting me, and I'm sorry I cannot be there in person, but I very much want to tell you about our results and that we characterize a novel mouse model. So I want to start by introducing my lab. And in the lab, we work on several animal models for developmental epilepsies. And what we want to do is understand the neuronal mechanism of these diseases and also develop novel treatment options. Most of our studies are related to Dravet syndrome, but we're also working on a Green2D-related developmental epilepsy. And of course, the focus of our talk today will be a mouse model for CHD2. So as Caroline was saying, these CHD2 mutant mice were generated in the Olitsky lab. And what they did was to introduce a frame shift, and this frame shift caused an early truncation mutation in the protein. And essentially, after amino acid 93, there is no more protein produced. So it's a severe loss of function. Only the initial part of the protein is being produced, but the rest is completely gone. And they generated this mouse on a black 6 background. And this is a standard mouse line that you use to produce mutant mice. And after they produced them, they contacted our lab and they wanted us to characterize their phenotypes as we did before for other mice. So we studied these original mice for about a year. And unfortunately, the conclusion that we arrived to was that did not have any phenotypes. So everything was similar between the wild type and the mutant mice. Now, this was very discouraging, and we were at a crossing point where we had to decide whether to abandon these mice, or maybe as a last resort, what we thought to do was to try and change the genetic background. So backcross them onto a different mouse line, hoping that it would unmask additional phenotypes. And the reason that we thought that it might help is that for Dravet syndrome, the genetic background really makes a difference. And on some mice, we have severe phenotypes, while on other lines, we have mild phenotypes. So this is what we did. We started crossing these black 6 mutant mice onto a 129 background. And we did this for several generations. And a generation in a mouse model is about 3 months. So we had to wait quite a bit before we could start studying them. And we started studying these mice while they were F5, so mostly over 95% already on a 129 background. And once we got there, first of all, we continued to clean the line, but we also started breeding them together. And while we bred 2 heterozygous mice together, we could get mice that are wild types, mice that have the heterozygous mutation that is similar to what you see in the patients, but also mice that have homozygous mutation. And the first thing that we did was to put an EEG electrode on these mice and record their brain activity. So what we saw is that some of the mice had epileptic events. So this is the wild type showing normal EEG activity in the mouse. And this is the heterozygous mutant mice. And you can see these discharges marked by these arrows, indicating some epileptic events. However, the epilepsy in these mice was very, very mild, and not all the mice showed these epileptic discharges. So if not all the mice are having epilepsy and the epilepsy is not frequent enough, it's very hard to quantify that. So what we try to do is to try to enhance their tendency for epilepsy. And we try to hit them up to cause febrile seizures. And we also put them in a dark room with high frequency flashes, and we try to provoke photic seizures. But unfortunately, in these mice, we could not evoke such seizures. Nevertheless, we had a lot of EEG recordings of normal background activity, and we quantified these events. So what we did was we take these EEG signals and we break them down into the different frequencies, and we measure the power or the amplitude in each of these frequency bands. And what we saw was that in heterozygous mutant mice, we had lower power all through the spectrum that we studied. So this is very nice because it enables a quantification of background EEG activity, and we're now studying what happens in homozygous mutant mice. Next, we looked at the presence of non-epileptic phenotypes. Now, human behavior is, of course, much more complex than anything we can get in the mice, but there are several tests that we can do and try to correlate between the phenotypes in the mice and what we see in the patients. And the first thing that we tested was motor functions. What we did was to pick the mice by their tail. And as you see here, wild-type mice tend to spread their legs, whereas the mutant mice tend to clasp their back feet. And this behavior was noticeable in the heterozygous mouse, but even more profound in the homozygous mutant mice. So this behavior indicated that there is a motor deficit in these mice. The next thing that we did was to put them in a box and measure the distance that they cover while exploring this novel arena. And here we saw that homozygous mutant mice travel longer distances and at higher velocities compared to wild-type and heterozygous mice. And this indicates that these homozygous mutant mice have hypermotor activity. Next, we were very much interested in their cognitive abilities. And we started with two common tests that rely on the natural curiosity of the mice to explore the arena that they're put in. So the first one is the Y-maze spontaneous alternation test, in which the mice are expected to study these mazes alternating between the arms. And the other one is the novel object test, in which the mice are introduced with a novel object and are expected to go and study this novel object that was placed. However, one of the problems with working with 129 mice is that they are notorious for being relaxed and lazy. And when we place them in these tests, they simply refuse to perform the test. So if the wild-type mice are not performing the test, there is nothing to compare to. So we realized that we had to do something else. And what we opted for was to test their ability to learn a motor task. So we used this rotor rod. This is a rotating rod, and we placed the mice on the rod for 3 days. And we allowed them to train for 5 consecutive trials each day. And we measured the time they're able to balance themselves on the rod. And doing this test, we saw that wild-type mice were all the time better than the mutant mice. And this time it was both the heterozygous mutant and homozygous mutant. So this indicates first that there is some motor deficit in the mutant mice, and also possibly motor learning is better in the wild-type mice. However, I do have to draw your attention to the fact that mutant mice are also improving on these tasks, just not as well as the wild-type do. So this highlighted that we also have a motor deficit in these mice and learning deficit possibly also. The next thing that we did was to look at their social interaction abilities. And again, the standard test is the 3-chamber social interaction test, in which mice can choose to interact with a stranger mouse or an object, but the wild-type simply refused to perform this test. So we opted for a different test in which we put 2 mice in an arena and we manually measured the time of interaction between them. And using this test, we saw that homozygous mutant mice tended to interact for a longer time with a stranger mouse. But most of this interaction was passive interaction, meaning that they would simply go together to the side of the arena and go to sleep together. But this result indicated there is a tendency for altered social function in these mutant mice. And the last thing that we tested is another artistic feature, and that's repeated behavior. So in the mice, a repeated behavior will be digging. And to test that, we put the mice in this arena with marbles and bedding, and we left them there for half an hour. And we quantified the time that they spent digging and also how many marbles they buried while they were digging. And what we noticed was that mutant mice were digging for a longer time, and also they covered more marbles while digging, indicating that these CHD2 mutant mice increase the repeated behavior of these mice and modeling autistic features in them. So to summarize what I've showed you, we've characterized a novel mouse model harboring a frameshift mutation in the CHD2 gene. And we have some specific phenotypes that can be used to evaluate the effectiveness of current and novel treatment options. And the readouts that we propose are, first of all, analysis of background EEG, as we have lower power in mutant mice. We can also look for motor deficits, cognitive deficits, and mainly correction of these deficits, and also improvement in repeated behavior that we see in these mice. So using these specific readouts, I hope that it offers a framework for further studies on effective treatments. And I want to finish by highlighting the people that actually did all of this hard work, and this would be Anat Mavashov, Shaket Tork, and Marina Bruzel. And I also want to highlight Igor Litsky and his lab who generated these mice. And I want to thank the rest of my lab, collaborators, funding, and thank you for listening.